The night sky and the lure of space have always pulled on the human imagination. But exploration did not really take place until the mid-1900s. But then it happened fast.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
Early space exploration was both competitive and collaborative, but the media really focused on the competition that was these heightened political tensions and an extension of the Cold War.
The reaction was one of astonishment and concern.
On Sputnik 1, the Soviet space satellite.
Research in space improved life on Earth from the very beginning, and today, the International Space Station is a symbol of global collaboration.
The amount of money spent on the space program is worth every penny. I think there are things we get from the space program that are valuable to our life on Earth.
I'm Krajnovic.
And I'm Myrna James. It's time to go behind the wings.
In this episode, we're going to explore the question, how did human spaceflight start, and how is it affecting us today? To start, we headed to NASA's Center for Human Flight, Johnson Space Center, to talk with NASA historian Jennifer Rothnazal. How did Johnson Space Center first get started?
In 1958, NASA was created.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
It was created as a response to the launch of Sputnik.
Today, a new moon is in the sky, a 23-inch metal sphere placed in orbit by a Russian rocket.
The first orbiting satellite around the globe. And Congress was very interested in establishing an organization to put a human being into space. And there was a group established called the Space Task Group. It was established about a month after NASA came into being. Its purpose really was to put a man into space. It was a manned satellite program. It became known as Project Mercury.
Project Mercury is the name given to the nation's manned orbital spaceflight program.
They were based out of the Langley Research Center, but that group formed the nucleus of what would become the Manned Spacecraft Center here in Houston. Once Kennedy gave his speech in May of 1961 that we were going to land a man on the moon by the end of the decade and return him safely, they realized they needed an actual facility, an actual center just for human spaceflight. Before that time, human spaceflight was seen sort of as a passing fad, a fancy. The deputy director for NASA at that time likened it to shooting a lady out of a cannon. And so it was sort of fortuitous that Kennedy proclaimed that we were going to achieve this amazing goal by the end of the decade.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
And so they started looking around at other locations all across the country, and Houston was one of those locations. So it was built essentially to get us to that final end date of landing a man on the moon by 1969. The individual who was in charge of the Space Task Group at the time heard that announcement and wondered, my God, how are we going to accomplish all of this? And he had to figure out how they were going to make all of this work in a very short time, in about 9 years. So that really was, a huge challenge. But NASA had been actually studying how are we going to get to the moon prior to this. It just, increased the pace. NASA was trying to figure that out well before President Kennedy made this announcement on the floor of Congress.
Now it is time to take longer strides. Time for a great new American enterprise. Time for this nation to take a clearly leading role in space achievement, which in many ways may hold the key to our future on Earth.
It was definitely a proxy war for the Cold War. If you look at the Kennedy administration, they had the Cuban Missile Crisis. They also had, some other missteps early on in the administration, and this was an opportunity for him to take something and get a win. How could he beat the Soviet Union? And this was something that they realized we might be on more even ground with the Soviet Union, sending a man to the moon and returning him at the end of the decade.
Hands joint leap, Apollo 11 lands crew on moon. The first Wright brothers flight was in 1903, and then it was only 66 years later when Neil Armstrong walked on the moon. in 1969.
A lot happened in those 66 years. The NACA, or the National Advisory Committee for Aeronautics, had been around since 1915, and people had already been thinking about human spaceflight.
These astronauts had to learn everything, every aspect of going to space, from rocket propulsion to orbital mechanics to what happens to the human body when they go to space, right?
So how did the first astronauts prepare to go to space, somewhere where no one had been before?
Astronauts train a lot, and so do folks in flight control. There's the saying that you train as you fly as you train. In those early Mercury flights, they did a lot of training because they weren't exactly sure what to expect. They put them through centrifuge rides up in Pennsylvania. They put them on the KC-135, which is a weightless aircraft. They did a lot of simulations of their missions, what they were going to be doing in orbit. Same thing with Gemini and Apollo. They were working through all of those missions and working through all of the requirements for their flight. They didn't just get into the capsule and go up in orbit and kind of see how things worked. There was a lot going on behind the scenes before anyone ever went up.
NASA has spent a lot of time throughout its history of going into remote environments and what they call analog environments. So to put astronauts or scientists in extreme environments all over the world. We know the ones, for example, like Antarctica is a classic. Back in the days of Gemini, Mercury, and Apollo, there was an interest in going into remote jungle areas. So the Air Force had a training program in tropical survival down in Panama. And so NASA contracted with the Air Force to bring the astronauts like Neil Armstrong, Buzz Aldrin, Michael Collins into that survival program. They went into the territory of a tribe down there called the Emberá, which was and still is a remote jungle area.
And so they went down to Panama at the Albrook Air Force Base. And they were working with the Choco Indians, so they were natives of that area. This was a really great cross-cultural exchange for astronauts and also for the natives in Panama. The idea basically behind Tropic Survival School was, first of all, to learn how to survive if, God forbid, your capsule came down in a jungle environment. How would you handle that?
We're in Panama, where it all started. The first NASA astronauts to walk on the moon were trained here for wilderness survival by the indigenous people, just in case. We've driven about an hour outside of Panama City, and we're about to get into a dugout canoe with a motor, and that's the only way to get to his village. We'll interview Chief Zarco there.
Ahí está bien.
Ahora vamos al museo.
Chief Zarco, tell me about your grandfather.
Estos son mi abuelo, la esposa y varias hijas de ellos. Dice también en verano que tocó la luna. Mi abuelo aquí muy joven, sí, muy joven. Y bueno, aquí tenemos otro que estaba entrenando. Nosotros acá le decimos balsa, cómo se amarra, cómo cortar. Entonces él le está enseñando. Lo que él enseñaba es a los 11,000 soldados y también a los astronautas.
People who were being trained to go to the moon and go into space acknowledged what they could learn from you and from your culture. Chief Zarco, what were some of the things that the astronauts learned here?
Cuando ellos subían a la luna, cuando ellos caían en la Tierra, ellos ya sabían lo que mi abuelo, lo que enseñaron cuando estuvieron en la Tierra, cómo sobrevivir, qué comer cuando ellos ya caminaban, cómo ellos podían tomar agua, fruta, qué fruta puede comer, qué fruta no puede comer. También tenemos como las plantas medicinales, entonces ya ellos sabían cómo hacer, en qué parte están, porque nosotros también utilizamos lo que es el sol, en qué parte estamos, entonces así sobrevivir.
Why is this area such an ideal place to train astronauts?
Donde nosotros estamos, el bosque es cerrado, hay muchos árboles grandes. También mi abuelo nos explicaba, cuando fueron a Vietnam, en ese tiempo, la guerra, en Vietnam es parecido a este lugar. Por eso que los americanos llegaron a este lugar. Entonces toda esa experiencia que mi abuelo le dio, ya ellos sabían, pero también compartiendo con los astronautas. Siempre en nuestra cultura, nosotros cuando uno muere, un envenenado, decimos, bueno, el envenenado ya se fue a la luna. Por eso que también cuando hablaron de la luna, viene la persona, bueno, voy a enseñar. Nuestro abuelo decía, bueno, nosotros vamos a enseñar todo para que también ellos conozcan.
You know, they had a lot of cross-cultural interaction with the Choco Indians, worked very closely with the chief, Antonio Zarco, and you know, encouraged them to get to know the folks as part of their training so that they would feel comfortable. And when they came back, they did a debriefing and talked about, well, what did you learn? And you know, they learned that the jungle isn't as scary as they thought it was. The most important thing I think that they walked away with was the fact that it was important to have this optimistic point of view when you went on a mission, that you weren't going to die if you landed in the jungle or desert, because they did desert survival training. You know, it was important to do the training, but to have optimism that you were going to make it out okay.
Some of the astronauts who trained in Panama actually were the ones who walked on the moon.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
The Earth, as it appears from the moon, is a very small and fragile object. And when you think about it, that's not an inaccurate description. Certainly a lot of the things that we do down here can affect the balance in a very fragile way. The greenhouse effect we're noticing today, for example, the changes between a healthy atmosphere and an unhealthy atmosphere are very subtle, very, very fragile, and you sort of get that feeling when you look at the Earth from a great distance.
Seeing the Earth from space can cause a significant psychological impact called the overview effect. To learn more, we spoke with cultural anthropologist Dr. Dina Weibel. Dina, it's so great to speak with you today. What is the overview effect?
So the overview effect is a term that was actually coined by a journalist, Frank White, who is also a researcher. When people go into space for the first time and look from their spacecraft to the Earth, the awareness that it's actually a planet, suddenly the borders are not real anymore. You see that they're imaginary. You see that everything is interconnected. You see the Earth as much more fragile. And a lot of astronauts have had this experience where it was like a sudden realization, something that caused them to rethink what it meant to live on a planet, rethink things like environmental awareness. Some astronauts have become really, really strongly focused on getting information out about global climate change and other things we need to do to protect the planet.
Steve Lindsay, I'm so excited to speak with you today, and I almost don't know where to start. You've had such an illustrious, amazing career.
I applied and was fortunate enough to get selected in 1995 to the NASA astronaut office as a pilot astronaut. So I spent 16 years at NASA, and while I was there, I was fortunate enough or blessed to fly 5 space shuttle missions, 2 as pilot, 3 as a commander.
That's amazing.
Yeah, I was very fortunate. My final flight was actually the final flight of Discovery. The trip in the space shuttle.
Go for main engine start.
Being on a launch pad to orbit is 8.5 minutes long.
We have main engine start.
Most 8.5 minutes of intensity you'll ever experience.
2, 1, and the final liftoff of Discovery. a tribute to the dedication, hard work, and pride of America's space shuttle team.
Discovery's 3 main engines are burning fuel at a rate that would drain an average swimming pool in about 25 seconds. The engines, combined with the solid rocket boosters, produce more than 7 million pounds of thrust. Standing by for separation of the twin solid rocket boosters, Discovery now traveling 2,695 miles an hour.
I'm picturing this extremely fast speed that you're going. And it makes me think of the overview effect. So what was that like? Did that happen for you?
I first saw the Earth on my first flight. We were, during ascent, we were probably 50, 60 miles high, doing about, I don't know, Mach 12 or so during ascent. So the rockets are firing, and we actually did this, what's called a roll to heads up, to shift from ground stations for communications to satellite communications during ascent. And I was in the pilot seat, of course, pretty busy. But when we did the rolled underneath, and I got my first view of the Earth. When you see Earth from up there, it does change perspective. I think it changes your perspective on how small the planet is. It changes almost everybody's perspective from an environmental standpoint.
Yeah, I remember one of the first times I looked out the window from space and I said to one of my crewmates, I said, what's that thin film over the surface? What is that? And they go, oh, that's the atmosphere. Almost looks like a contact lens over somebody's eye, how thin and fragile it is compared to the size of the planet, which is kind of scary looking because it's, the most important thing to our survival is our atmosphere. I think makes you more kind of in tune with, environmental causes. I remember the rainforest in South America looked different on my first flight than it did on my last 17 years later. And then when you look at the planet, you don't see political borders. During the daytime, you do at night a little bit. Countries, sometimes use different kind of light bulbs, so it's easy to tell. I'm on the International Space Station, but we're really all on a spaceship traveling through space called Planet Earth, and we're all part of the same team.
I know that you were on the International Space Station for basically a year. How did that come about?
Yeah, I was there for nearly a year. We launched in March of 2015, landed in March of 2016. It's one of the greatest successes of the International Space Station program is that you can have two countries that, historically can be at, not on the most friendly basis, unfortunately. You can work cooperatively on something that's probably the most challenging thing we do and demonstrate that we can work peacefully together as a team, and space is a perfect place to do that. And for us, our relationships as crew members, we have to rely on each other for, friendship, for help with our work, and literally at times for each other's lives.
Out of that competitive atmosphere that defined early space exploration came a whole new vision for collaboration. And then the International Space Station, and so many countries are involved.
The International Space Station, it's truly that, international. You have 258 astronauts that have been there from 20 different countries. And then when it comes to the countries involved in the ISS, I mean, this is going to test my geography more than anything, but we've got the US, we've got this big one.
Right, Russia here.
Russia.
Enormous.
We had Canada. Canada's up there.
We have Japan right here.
Japan, yep.
JAXA is very involved with space activities.
And then, you have the European Space Agency, which is going to make up a lot of the countries. Belgium, Denmark, France, Germany, Italy, the Netherlands, Norway, Spain, Sweden, Switzerland, and the UK.
The International Space Station is just that. It's truly international. It's almost like in space, where borders don't exist.
The idea was that this would be a good way for NASA to get experience working on an International Space Station. That was the goal, to have our own space station. We had our first space station, Skylab, but this was going to be a little different. So this was an opportunity for astronauts to get some experience working on board a space station, kind of this building block for NASA. The international aspect of space station has been so vitally important. That's probably the most important legacy that space station will have. Many of the pieces of hardware, for instance, never met on the ground. The first time they met was up in space. And so just working together, I think it's so vitally important. We may not be able to do it on the ground, but in space we've been able to do it so successfully.
Hi, this is Steve Lindsay, commander of the Space Shuttle Discovery. Welcome.
You know, when you look at the space station and the international partnership and 16 nations up there working together all the time, that all gets blurred, and we're generally speaking one team up there. If you'd have told me when I was a pilot in the Cold War that within 10 years I'd be flying with Russians, I would have told you were crazy. But that changed.
Right now the plan is to deorbit the space station around 2030, right? And eventually you're going to have to do that. I mean, things age, they age in space. You got on a spacewalk on the space station, it's surprising just how beat up it is outside. And the sun is just brutal. The changes of temperatures of, plus or minus 270 degrees. Thing gets hit on the outside. There's a lot of holes on the outside. Fortunately, so far those holes haven't penetrated the pressurized volume, but there is a lot of damage to this. So eventually you're going to have to put it in the Pacific Ocean.
One of the most important things that came from that experience was the twin studies, because you have an identical twin brother who's also an astronaut.
Yeah, because my brother and I were identical twins, we're genetically very, very similar, almost like, 99.9% genetically similar, that they felt like that they could get some good science data.
So the NASA twin study, the idea was born to try and get more genetic information and more molecular information and other types from people in space for longer periods of time. That's a little bit complicated to do, so what they thought was if we're going to use very small number of people, that they should be twins. That would allow us the ability to study one twin in space and the other twin on Earth. Doing that would allow us to better understand the differences that weren't related to genetics, right? Because they should have a fairly similar genetic profile.
For something to be statistically significant, you need a lot of samples.
Right.
And this is kind of a sample of one. Having said that, it's also a longitudinal study, so you can get statistically significant data by studying the same thing over a long period of time, meaning Mark and I.
So the goal was then to study them for 1 year, and Scott Kelly was the astronaut who was in space. And so both of the Kelly brothers gave enormous amount of time, willingness, blood samples, every kind of tissue we could get, psychological testing, physiologic testing, over that entire year period. And so at the time it was really the longest and most comprehensive scientific study that had been done to that point.
So that became part of the science program, and it got the most attention, more attention than the other science, which was actually probably more important, but just didn't have that kind of like cachet, human interest cachet that a story about two twin brothers doing a science experiment on the space station had.
Give us a few nuggets of the results of the twin studies.
Well, there are a lot of experiments, and I didn't give these experiments any more attention or less attention than I did everything else that we were doing. To the researchers, all of them, their science is the most important. And during the course of that year, we had 400 different experiments going on the year I was on the space station.
That's incredible.
Yeah, so this was, I don't know, it was probably 10 or 15 different studies. Some of them were on human cognition, like how does your brain change over the course of being in space from your ability to perform certain tasks and functions. What we would do is, I would collect data, or mostly it was like science samples, but there were tests that I would do, and then my brother would do the same ones on the ground. And I'll tell you what, you got to give him credit, because he didn't even work for NASA. I think they were going to pay him, but it was like so little that he said, don't bother. I don't want to deal with the tax headache from being paid, it's just really small amount.
So why is space exploration so important?
I think it's important for a number of reasons. We are, genetically speaking, I think explorers, right? If we didn't have that gene, we would still be living in a cave somewhere. We have this desire to see what's, over the horizon, what's over the ocean, what's in outer space, and what it gives to our society, to our economy, to our national security is worth every penny.
If you look at history, that's what human beings do. We've always explored. Well before Christopher Columbus, you know, well before the Vikings. That's just something that human beings do, and I think that's just a continuation and an extension of what we've done in the past and will continue to do. And it's extremely important, it's extremely vital, beneficial to the American public, to the globe.
As space exploration transitioned to becoming more collaborative, it set the stage for how it can benefit life right here on Earth. But it's not just about going outwards, going to the moon. It's also about looking back at Earth. What can we learn about our own blue planet?
Looking back at the Earth from space gives us a whole new perspective on our planet.
Humans have always had the impulse to explore towards the night sky, towards the cosmos, towards the unknown.
Thrusting outward into space, we gain new perspective on ourselves.
But it's not just about going as far as we can. Space exploration also provides a unique vantage to look back at Earth, all of Earth, in near real time.
Exploring space, we learn quite a bit. We learn about our home planet, we learn about our solar system, we learn about our universe.
Sensors on satellites have revolutionized the way that we understand the Earth. The data is used for measuring snow cover, infrastructure in cities, mapping. There's a lot to explore.
The technology has increased in capability, has decreased in size and cost, and that enables a lot of things to happen.
I'm Krajnovic.
And I'm Myrna James. It's time to go behind the wings. A big focus for NASA and players throughout the industry has become our own planet Earth. So today we're going to focus on the question, what can we learn about Earth from data from space? To start, we'll talk with Dr. Kate Calvin to learn what NASA Earth is all about.
One of NASA's most important missions is our home planet, Earth. And we have a lot of research going on about Earth, from observations to models to technology. We measure the Earth on and above the Earth's surface so we can see the state of the Earth and how it's changing. We build computer models that help us understand Earth. They can both help us understand the processes that are impacting Earth. They also give us a window into the future so we can see how Earth might change going forward. So you think about some of the pictures that astronauts have taken from the Apollo missions or from the International Space Station, and you see Earth. You see this beautiful blue ball with clouds swirling around. And our satellites help us take those sorts of images nearly continuously and looking at all of the Earth. Each satellite is designed to measure something different. So some are looking at visible light, some measure changes in gravity. And we have more than 24 of these satellites and instruments in orbit. And together they let us see things like vegetation, carbon dioxide, clouds and precipitation, changes in the mass of ice sheets, and much more.
The satellite era in the grand scheme of Earth science is relatively recent. Started just after the launch of the Sputnik satellite in the late 50s. Into the early 60s, it was very experimental. There was a lot of funding for developing rockets and thinking about how to put people up there. In terms of the instruments that could view our Earth, that was a little bit secondary. Well, the first cameras that went up were analog. Film canisters were dropped from space down and being collected by people. Into the 70s, then digital technology started to come online, and that was really exciting because it allowed us to start to do some really fancy things like send out microwave signals with timestamps on them, which we use to power our global positioning system, or GPS network. Right, so we've come a long ways as our scientists in the use of satellite data. Right now, it's indispensable. It's difficult to imagine how science would be undertaken without satellite instrument measurements.
We've been collecting observations about the Earth from satellites for decades, so we can see not just the state of the Earth today, but how it's changed over time. One of the satellite programs that we have in partnership with USGS is called Landsat. And Landsat lets us see land use and land cover. So we can see where there are forests, where there are urban areas, where there are crops or snow. And we're coming up on our 50th anniversary of Landsat, so we have nearly 50 years of observations of land use and land cover. So we can see how that has changed over time. And when you look at Landsat records, what you'll see is expansions of urban area. You'll see declines in forest in parts of the world. And we have other satellite missions like that that give us different information. And we work with a lot of the commercial partners. So we actually have a commercial small sat data acquisition program where we buy data from some of the commercial small sats and make it available to NASA researchers so that we can do more climate research, more Earth science research using other satellites, not just our own missions.
Satellites are constantly orbiting the Earth, and you probably use them every day, whether you realize it or not. We're about to use GPS, or the Global Positioning System, to head to Maxar's headquarters. We're going to meet with Dan Nord to learn more about satellites and their sensors. What can we learn about the Earth by looking back at it from space?
We think about that every day, and the answer is a lot. And so we have an ability to look at a holistic scale at the world and monitor change. And since we've been doing it for 25 years, we actually have change over time. And with that, you can model a lot of behavior. And then if you look globally, it's, where's the next big city growing up? We can answer that. The life cycle of a satellite is fascinating. And first, you need to figure out what you want to do with your satellite. And so we make high resolution Earth imaging satellites. We also make satellites that help with communication, whether it's Wi-Fi or other, and then multispectrals. And then you have to build a satellite, and this is the hardest thing. This is more like building a Ferrari. This is custom built, hand built, large scale technology that cannot fail. You can't go fix a satellite once it's up. There are some companies starting to think about how to do it, but the thing's moving thousands of miles an hour far away. So everything has to be checked, double checked, and quadruple checked.
So yeah, let's take a look at the satellite. It's got a couple different parts here. I mean, on the sides, I know you said satellites don't have wings, but what's happening on the sides?
Those are solar panels that brings in the sun's energy to power the vehicle. But this doesn't have wind resistance or anything. Solar panels can't fly.
They're not going to provide lift.
And then if you look up here, this is the camera. So this is actually inverted, aiming down at Earth.
So we have our power source, this would be our sensor, and then I imagine somewhere on here is a communication device to actually transmit that back to Earth.
There you go. Yeah, and so it's flying, taking pictures, and in real time sending the data down to our ground stations. And you've seen, what a generic ground station looks like. It's a dish looking straight back up. Space is hard, and what it's reflecting is just how complex building machinery that needs to withstand extreme temperatures on the hot side, extreme temperatures on the cold side, radiation. There's so much you have to protect against, and it has to work every time. You then, pick who's going to launch.
There we heard the final call. LD is go for launch.
And we have liftoff.
The last one we did for Sirius XM was on a SpaceX rocket. And then once it's up, they put it in the orbit that we ask for, either low or mid or high. And then we take about a month to get it into place and test every single element. And once that's done, we start pulling imagery down. These are big imaging satellites that can capture all of Denver in one pass, but then can zoom in and look at an individual vehicle with enough resolution to know what's the make and model, which is incredible. And then when it's time to decommission a satellite, you put it in a drag orbit and it burns up in the atmosphere.
Over 4 billion people are using Maxar technology every month. People are probably interacting with satellites whether they know it or not on a daily basis.
The way mapping works in the old days was you had to physically go to a place. And even Google, when they did their first mapping, they drove cars all around the world. Whereas a satellite can do it relatively quickly.
I do want to focus in a bit because there are so many examples. Tell me about the work you do with the Jane Goodall Institute with chimpanzees and mapping and conservation.
From space, we can count animals. It's absolutely fascinating. We've done it with narwhals in Canada. With the amount of imagery we have over time, we can monitor their habitats. You always hear the stories, this population is dying. We can count that and check it and turn it into real ground truth, real fact. So we're looking for these use cases because this is new technology at a global scale. What can we use it for? We're getting really close, up close imagery where each pixel is about 30 centimeters. We understand what's happening on our planet. The observation and the crunching of these massive chunks of data. So we have 125 petabytes of imagery that we store and process, and we add to every day. I think it's 3.5 million square kilometers of imagery every day of the Earth, and we pull it in and we process it. We can run algorithms that say, hey, actually this corner of this place, it's going to be a drought in the next 5 years. That's information that's invaluable for either these companies or these nonprofits that want to help.
Here we have a map that shows SAIL, the Surface Atmosphere Integrated Field Lab, focused really in the Colorado Rocky Mountains. And it's a big watershed. It's got the Continental Divide, and that means a lot of people depend on it for water. It's a big area. They're using these satellites, but the satellites alone aren't enough to get verified data and to really see the big picture. That's something called ground truth.
Yeah, we definitely need ground control points so that you can verify on the ground, as you said, ground truthing the data from space to show that they're in the right place on the ground. That's really essential for any kind of scientific data like this.
We've made it to sunny Crested Butte, Colorado. We're about to head to the top of the mountain and check out one of SAIL's observation towers. They're using more than 50 sensors, taking measurements from bedrock to satellites in space. Let's go see how it works.
Water is life, and it's something that we rely on, and a lot of our ecosystems rely on as well. We're here in the headwaters of the Colorado River, the major river system of the western United States. It serves about 40 million people, and the water for that river comes from snow that we're seeing here in the mountains. We're getting a lot less of it. We're here to make some very detailed measurements of how that change is occurring. So we are midway up the mountain on Crested Butte Mountain Resort. We are at the mountain site of the Surface Atmosphere Integrated Field Laboratory, or SAIL campaign. So we can learn a whole lot about the Earth from space. I have had the privilege of working with a lot of satellite instrument data sets, and it's really remarkable because they're so powerful. One instrument smaller than this trailer is able to measure the entire planet. At the same time, the ways that we measure snow is from satellite. That's actually a real cutting-edge problem, something that NASA is definitely still working on. We're providing a great set of observations to help inform a number of the researchers on SAIL who are thinking about how to design what that satellite looks like. And the reason it's so hard is because just looking at where snow is doesn't tell you the whole story.
It's such a complex problem, and it's really about seeing the big picture from every different angle, from space to underground to 50 different sensors. And we're at one of the study sites. We've got a couple of them right here. Let's go take a closer look at the precipitation radar.
Inside that radome, that ping pong ball, is an antenna that spins around and sends out microwave energy at wavelengths about 3 centimeters. It's very sensitive to how much rain is falling or how much snow is falling. This instrument measures the input of water into watersheds that serve the Colorado River. My colleague Ken Williams will talk a lot more about water accounting and why that's such a big deal.
How are some of these instruments working in conjunction with satellite imagery or balloons going into the atmosphere and some of the other data points that you guys are collecting?
Absolutely. What we're going to be taking a look at is called the aerosol observing system, and what it's really trying to do is to measure the particulates in the atmosphere. You can see that deposition or that distribution of dust from things like balloon-based measurements, from fixed-wing aircraft, and from satellites as well. It's what we call variations in albedo. And so how white the snowpack is versus how dark the snowpack is really important in terms of how this melts out in the spring and how that meltwater finds its way to our local streams and rivers.
That is so cool. Dust is so small, but you can still see it from space.
That's absolutely true. It may be small, but it can have a really outsized impact on how snowpack and mountain snowpack behaves. And so this is the first place in the United States that allows us to link atmospheric processes, where, when, and how precipitation is falling and occurring, and how that precipitation finds its way into local streams, rivers, and into deep groundwater as well. The Aerosol Observing System. Let's go take a look at it.
Thank you. See, that's why you're the scientist. All right, let's look.
With the rise of climate change, increased stress on plants, we're actually really interested to understand how atmospheric processes play a role in delivering a critical element like nitrogen to these watersheds. Well, what that's really allows us to do is now to link satellite-based imagery from the Landsat satellite products to really look at the greenness of our forests, okay? And greenness is really a proxy for forest health. So we can go back over a decade of Landsat satellite data and look at how these forests are either increasing in their greenness or decreasing.
I've done field work measuring trees, and I spent a week measuring trees with a colleague, and we measured the width of every tree to give us a sense of how old it was and how much carbon it was storing. But we covered a very, very small amount of trees in our week there, where a satellite can cover the whole surface in that same amount of time, all of the Earth. And so they kind of work together though. We use the ground-based measurements to calibrate the satellites. We use the satellites to fill in the spaces and times that we didn't have ground-based measurements.
Wow, I can't even count how many sensors we've looked at already, but we've got miles to go before we sleep. And if the weather's good, we might even be able to launch a balloon this afternoon. Let's pop the skis back on and do it.
Let's get them on.
Here we go. Gothic, Colorado is a former mining town outside of Crested Butte that is now used for scientific research. And in the winter, it's only accessible by cross-country skiing. A few miles later, we arrived at the Gothic Research Center. So this is really cool. We're able to see from space pretty much where we're standing right now. I mean, you can almost see us right there.
Yeah, right?
Not quite, but...
Well, you know, if we put our hands out, maybe, you know?
The satellites are giving context to all the sensors and work being done on the ground. And just like there's sensors here on Earth, there's also sensors up on those satellites.
Absolutely. So what we're seeing here is we're seeing in these imagery where the extent of where the snow is. But that doesn't actually tell us how much water is in there. And so a lot of the measurements here are getting at those details of how much water is in the snow that we're seeing here in the imagery. We are looking at the imagery that was collected today of an instrument called MODIS, which stands for the Moderate Resolution Imaging Spectroradiometer, so kind of a mouthful. This is on the NASA Worldview website that shows all kinds of imagery. It's super powerful. We know it's from today because we can see this black spot here is where the satellite data hasn't actually collected information yet.
What's at stake with these measurements?
It's what's at stake is the development of a predictive capability for how much water we're going to have in the future. We would really like to know if there's going to be enough water for all of us this year, next year, 5 years from now, 10 years from now. Without really going to these places and seeing what's actually happening on the ground, we're not able to know if any of our predictions have value.
We're getting ready to do the balloon launch. What exactly do you do to get ready and launch the balloon?
First, we prep a sonde, and this is one of your sondes here. We use this computer software here to condition this, and we basically calibrate it. So it has a relative humidity. We compare this sensor in here to a sensor inside here. Same thing with temperature.
And you make sure it's accurate.
Exactly.
Okay.
Yeah.
And the balloon is kind of just the vessel to bring it. How high exactly do these balloons go?
Say 90,000 feet. It sends via a radio link every second.
Okay.
So we get a download of height, temperature, relative humidity, and location, and it gives you some wind.
So we've got our helium balloon and a bunch of sensors. Yep. Going way, way up.
Yep.
All right, here we go. Launching. The weather balloon will rise into the mesosphere about 17 miles high, whereas the commonly agreed definition of space is around 62 miles high. Together, measurements from the weather balloon, the satellites, and all of the other sensors will help the sail team learn more about mountain watersheds. Water is life, and snow is life too for the 60 to 90% of people worldwide that depend on mountain watersheds for their water. We've made our way down to the Slate River, one of the tributaries to the Colorado. And even within the US, that's 40 million people that rely on this water. Now it turns out it's really hard to predict how much precipitation there's going to be in the mountains and how much of that's actually going to make its way into the river. And that's why SAIL is collecting an unprecedented amount of data from satellites orbiting right now all the way to underground to try to understand and actually predict the future. How much water will be here in 5 years? And that's a really important problem to solve.
This chart shows the increase in the number of operating satellites that exist right now. In 2006, there were less than 1,000. So fast forward to 2020, there were less than 3,500. And really, this number is going up exponentially with all the different satellites that are being launched, tiny little nanosatellites and small sats, especially the ones for global internet services that are coming up.
We're continually thinking about what we're going to launch next, what we want to measure next, which science questions we need to answer. But we're also working at the same time to design what's called the Earth System Observatory. And this is a set of satellites that are going to work together to provide a 3D holistic picture of the Earth from the surface up through the atmosphere. The first satellite in that will be a satellite called NISAR. And NISAR is going to let us measure changes in the Earth's surface at a fine level so that we'll be able to see things like ice sheet collapse and landslides. Satellites are really critical because they provide us continuous observations and they provide a large extent. So many of our satellites are global in scope, so we see the whole Earth, not just the area right in front of us. And that's really important because climate and Earth science, it's a global research area. And so the more we know about the entire Earth, the better we can understand Earth and the better we can think about how it might evolve in the future. And the satellites that we're designing and planning to launch in the future will provide even more information and give us a better sense of where we are and where we might go. So our data is, people use it around the world, from scientists to decision makers. And a lot of what we do when we're thinking about future missions is think about what questions do we have? What do we want to know about the Earth? And work from there to design a mission that can help answer that. So we know more than we ever have before. And every year we learn more. We keep developing new technologies and sensors that'll give us the ability to understand even more about the Earth, from heights of trees to how much snow to sea level rise, changes in ice sheets, carbon dioxide. So we know so much about the Earth, and the more we learn about the Earth and the more we understand the processes that affect it, the better we can plan for the future.
Now we're looking at a map of satellites in orbit. There's over 19,000, and if you scroll around, you can kind of see, they kind of look like they're everywhere, right? And then you zoom in, lower Earth orbit, there's even more. So they're at different altitudes, they're at different orbits, they're all spinning at once.
This is the live map that shows where they really are, and you can see the concentration in low Earth orbit.
And what's interesting is if you flip the type to junk, it turns out over 13,000 of those 19,000 are not operational. They're junk, they're old, they're not being used anymore. The not junk is only 5,000, so there's way more junk satellites up there than operating satellites. And if you play that out, you know, over time, there's just going to be more junk, and you know, it raises these questions. How do you get rid of them safely? How do you avoid collisions? You know, when two objects collide in orbit, it creates thousands of small pieces, and all of those small pieces can then impact again, collide again with other objects in space. So the worst case scenario with space debris is that you kind of create a belt of space debris all around Earth, and that makes it pretty hard to leave orbit. So it kind of shows how serious this all can be. Thankfully, there are some companies today starting to work on that.
My name is Eric Ingram. I'm co-founder and CEO of Scout, and we're a company developing space domain awareness and vision capabilities for satellites to be able to navigate autonomously, so essentially by themselves. So the way we currently track things in space, be it satellites or debris, is primarily with Earth ground-based radars and telescopes that track the traffic going overhead in space to determine which dot is which satellite. As the number of satellites up there increases, that becomes more difficult. So what we want to do is be able to better track all of that to, again, make space a safer place to operate in. the cost of getting to space and the cost of all the technology is decreasing, and the capability of that technology is increasing. Just like your cell phone can do a lot more now today than it could 10 years ago. And the same thing is true with satellites. You see Earth observation, communication satellites, internet providing satellites all going up in the near future, and that's changing the way space is operated in. And so there's a lot more satellites up there that are using space to get all of these amazing services down to Earth. And companies like ours are working to make sure the space traffic is navigating in a safe way and that everybody's able to use space to provide these services to Earth.
Not all satellites have fuel on board to move, and so who has the right of way? What happened on the roads, and then the seas, and then the sky, we're going to see replicate in space. So as things get crowded, you have to pay attention to directing traffic. You need to pay attention to cleaning streets. So all of these are going to have analogs in space. It'll be a smaller scale at first, but everything is moving really fast. The commercial and government collaborations have created these companies like SpaceX, which are bringing business practices. I mean, now we can put things in space at volume to start really exploring the world and making second and third homes for humans. It's a really exciting time.
Space startups are filling in for services that weren't even possible a few years ago and are more necessary today than ever before.
More satellites and sensors in space provides us with more data than we've ever had before and more insights about the Earth. It also means that we need more infrastructure to support this increase in activity. Historically, public space agencies have defined space exploration. As of now, in 2022, 77 countries have space agencies.
For the first sort of 50 years of NASA's existence, NASA was the customer and the private sector was the supplier.
Now, billionaires are fundamentally changing the public's relationship with space.
We've seen the rise of a lot of small companies and startups like ours that establishes a whole ecosystem.
And a booming space economy in Colorado and beyond is really starting to take off.
Moving manufacturing off of our planet, creating opportunity and future for everybody, that's what I want to see.
I'm Krajnovic.
And I'm Myrna James.
It's time to go behind the wings. So in this episode, we're going to explore the question, how is a growing space economy changing what's possible in space? To start, we talked with Phil McAllister, NASA's director of the Commercial Spaceflight Division for Space Operations.
When we first started talking about shifting some of the responsibility for low Earth orbit onto the private sector, I think there was definitely a sentiment within some parts of NASA that we were giving up something, something that was special and core to our mission. And over time, I think that sentiment has really reduced as people have realized that if we were always limited to NASA's budget for what we could do, we would always be somewhat constrained. For the first sort of 50 years of NASA's existence, we kind of interacted with the private sector one way, which is NASA was the customer and the private sector was the supplier. So we would write very detailed requirements, we would make all the decisions about the spacecraft or the transportation vehicle, and then we would hand those to the private sector and say, go build this. And we would be sort of in charge, we would make all the decisions, and we would own the resulting hardware. But today, what we found is the commercial space industry, which is an industry looking to sell not just to the federal government, but to other organizations and to other just consumers. When you have a thriving commercial space industry, it doesn't necessarily make sense for NASA to build everything from scratch. We can leverage the capabilities in the private sector. That's kind of what we mean by commercial space. And I think just within the last 10 years, these kind of partnerships have become possible.
Previously, the space industry has been very large company driven. You've got your large primes and government contractors, and that was how it was for 50 years. As technology has increased and as the price and cost of getting to space have decreased, that has enabled many more businesses that now can close their financial model. You've seen the rise of a lot of small companies and startups like ours who see needs in the market and needs that the industry has, and we're able to meet them in ways that larger companies it might be more difficult to. And so that establishes a whole ecosystem of everything from single-person startups all the way up to 1,000-person companies.
Dylan Taylor, thank you so much for being here with us. You, I think, have more passion for space than anyone I've ever met. So you're currently the founder and chairman of Voyager Space Holdings. Tell us a little bit about the company.
Voyager Space is really purpose-built to help scale what we call new space, which is the innovative entrepreneurial sector of the space industry.
There's obviously a lot of collaboration in space, but what role does competition play?
Well, I think the market forces help, right? I mean, I think SpaceX was born out of competition with the Russian Soyuz rocket, with Boeing, with Lockheed, and because of that, they were able to attract third-party capital and invest and innovate. So I think it's really important. I think the market forces work. When space was purely a nation-state opportunity, you didn't see the level of innovation. We certainly didn't see rocket reusability. And now we even have things like launch as a service, where customers just simply pay to be inserted into a particular orbit. We are in a renaissance for the industry. The level of innovation is just shocking. And I expect more to come.
This is a graph of the investment totals in space. Just look at that graph. I mean, it's straight up practically. In the past 20 years, the global space economy it's grown from just over 1 billion to over 16 billion. That's huge.
Yeah, in investment in space, private space companies.
And then to get a sense of where this is going, this is looking at the future. Here we are, 2022. And the chart just goes straight up.
So the global space economy is expected to grow 4.5% in the next 25 years, and that's exponential growth, and it's not going to slow down anytime soon.
When you look at it like this, it makes it seem like we're really just at the beginning of things today. Mm-hmm. So we made our way to Lunar Outpost to learn how they're using technology originally developed by NASA to test for lunar dust to actually improve air quality here on Earth. Now that might sound a bit confusing, but we're going to talk to their CEO, Justin Cyrus, to learn exactly how.
My name's Justin Cyrus. I'm the CEO here at Lunar Outpost. It's been a very good past couple years for startups in the community, because now instead of just straight competition against the likes of some of the big names like Lockheed Martin, Northrop Grumman, or Boeing, they're looking at ways that they can work with small startups like Lunar Outpost and Outpost Environmental to innovate quicker and to not only bring value to the aerospace community and what we're doing out in cislunar space, but to find ways to bring that technology that costs a lot of money to create back here to Earth. So NASA spin-offs are technologies that originally were funded out of NASA or a part of a NASA program. And what these spin-offs are is commercial companies working with NASA to find ways to take this tech that folks have spent a lot of time and money on, and finding ways it can benefit life here on Earth.
So speaking specifically about the Canary sensor now, we actually have one of them right there behind you. What was the original application of the technology?
So the original application of the Canary sensor technology was actually to detect lunar dust. So it's called lunar regolith, and it's extremely fine dust. And it's harmful because of the chemical and geometric composition to not only humans, but robotic systems and space stations.
What was that technology transfer when you realized, okay, maybe this tech could be useful to improve life on Earth?
Some of the key core technology is detecting a particle and figuring out what's in that particle, or detecting just what's in a concentration of air. So what we do with the Canaries actually here on Earth, actually figure out what's in the air real time out in the field. One of the use cases that was highlighted by City and County of Denver was putting it next to schools. So figuring out how we can improve the air quality for kids in elementary school, middle school, and high school, and the effects of the study are still being seen today. We were able to collect real-time data And air quality was worse than you would want it to be, especially for elementary age kids at some of these schools. So that's just a small sample of what City and County and Denver was able to do with the air quality data we collected. The first day we actually put a canary on an oil and gas site, we found a methane leak within 7 minutes, and that leak was fixed within the first 2 hours. Whereas the historical way of doing it would have been months later until they found that leak. And at that point, thousands of liters of methane would have already been dumped into the atmosphere.
If you don't measure, you'll never know, and with the canary sensor, it's just that extra layer of data.
I think that's very well said. If you don't measure, you'll never know, and if you don't know, you can't fix it. And certainly that is what we're trying to accomplish by providing data not only to the companies, right, the oil and gas, the chemical processing, but also to the regulators so they can make sure the air we breathe is safe, healthy, clean. Because we have a lot of really cool tech that we're working on in space that can be brought here to Earth and applied in those markets. And what that strategy has allowed Lunar Outpost to do and accomplish is to reach some of our more ambitious goals of putting a rover on the moon, of making oxygen on Mars, while still driving profit, revenue, and having that strong near-term positive impact that can be seen from the canary sensors.
There are thousands of spin-offs from NASA, many of them that we use every day.
Things like sunglasses, rechargeable batteries, even sneakers.
Hundreds of NASA spin-offs have come directly from the International Space Station. We spoke with former astronaut Scott Kelly, who spent nearly a year on the ISS.
I think there are things we get from the space program that are valuable to our life on Earth. If we didn't have a space program, we wouldn't have these cool cell phones in our pockets that we look at all the time. So there are a lot of those kind of technical things we get from it.
The space program has created great benefits in terms of technology, spin-offs for use on Earth. I mean, one of the most obvious is actually solar power, which some people think will be our salvation from global warming. Solar power was developed as a really usable technology for use on spacecraft, because if there's nothing further off-grid than a spacecraft. And my little company has also spun stuff off. We were interested in making fuel on Mars that required capturing CO2 out of the atmosphere, and a number of other technologies. And it developed our gas capture technologies for a number of purposes, one of which has been to capture gas being flared by oil wells so that they could be trucked off to market instead of being flared. And another was capturing CO2 out of fermentation vats so that breweries could use the CO2 from their own fermenters instead of having to buy CO2 from industrial sources while venting their own CO2 to the atmosphere.
Here we are at the Denver Beer Company. We're going to learn about tech transfer from NASA, and they're creating technology where they're learning about resources that we have and how to use them here on Earth. So you're wondering, space, beer, how do they come together? We're about to find out.
When the beer's fermenting, there isn't really a great way for small craft breweries to capture that CO2 until Earthly Labs invented this CC machine. And so they licensed this NASA technology, which allows us to capture the CO2 during the fermentation process, bottle it up, and then we can reuse that CO2 later in the process, or sell it, or do whatever we want with it.
All right, so let's go check it out.
Okay, let's go check it out.
Great.
We've installed some piping that pipes the CO2 into the CC machine, where it's filtered, cleaned, cooled down, and compressed, and then put into a big 750-pound container. It tells us how much CO2 it's captured, the pressures, the temperatures, and everything that we need to know to run it.
Our third partnering business came in, and actually an indoor agricultural business who needs CO2 for the production of plants. So by partnering Denver Beer Co., who generates CO2, with another business who utilizes CO2, we were able to get through the pilot program. It was wildly successful. Really what we hope to see is a snowball effect, that people look to this as an example that other breweries can say, I should be capturing my CO2 as well.
Space has limited resources, but I guess our planet does too.
sort of like you can't really ship things to the ISS all the time, or to the moon, or to Mars. So they need many, many ways to utilize resources that are already there. So that's what the in situ resource utilization really is.
So thinking about this increase in public-private partnership, we've talked a lot about the startup side, but what does it enable NASA to focus on?
The public-private partnerships not only allows the aerospace community to reach these business plans that wouldn't otherwise be possible, but it also allows NASA to reach far greater goals than they could otherwise. A great example is the Artemis Program. Getting humans to the moon on the budget that NASA currently has is not possible, it's not feasible without the public-private partnerships that have been put in place. But in addition to that, NASA is the cutting edge of space agencies around the world, right? They're looking at not only getting to the moon, but further getting onto Mars and exploring other planetary bodies in our solar system, and with the James Webb Telescope, many solar systems beyond our galaxy that would not otherwise be possible if they weren't working with the commercial industry.
By being able to shift some of this responsibility and have the private sector pick up some of these costs, we can go further, faster. And I think there's always going to be a role for NASA. That's our job, is to push the bounds of exploration where you don't necessarily see an economic potential. It's really just been over in the last 15 years that we've seen these very, very successful partnerships. And now, particularly with the Crew program, we have seen all kinds of benefits from that. Just within the last 12 months, we've seen an all-private mission just to orbit, the Inspiration 4 mission, which was really remarkable, first time in history. And now today, we have 4 private astronauts on the International Space Station, living and working in space on the ISS. Another thing that is a historical first. And I really do think we are at an inflection point with human spaceflight, and it's really about to take off.
Skip, I'm Cray. Pleasure to meet you.
Nice to meet you.
Let's talk about space.
Yep, sounds good.
Let's do it. We're almost in this new era, this new space economy. There's more private companies than ever. They're collaborating with national space agencies. How has that impacted space law?
Well, a couple of things that are happening now. I represent a private astronaut who's going up. It's a SpaceX flight up and back, and NASA hosts the private astronauts, and a company down in Houston called Axiom Space put it together. It was really a first of a kind contract. You can imagine a lot of legal issues associated with sending a private person up into space for 10 days. You know, this isn't a suborbital flight of 6 or 8 minutes. This is 10 days up in space.
Thanks to our SpaceX team for getting you there. My thanks to NASA for hosting us, and to the entire crew. You know, we've been talking about this history-making mission for a long time.
So you've got private astronauts going up now to the International Space Station, and you've got NASA planning for commercial space stations before the end of this decade.
The ISS is getting old, and we would like to retire it by 2030. That is NASA's policy right now. So the good thing is that gives us a little bit of time. We are currently working with 4 partners to design, develop, and hopefully deploy prior to 2030 their own commercial space stations. And the long-term vision, I believe, at NASA is that I will be able to just buy a ticket, just like anybody else, and go up to a destination in space, do my work, and come back down.
Right now, we are on contract with NASA for a commercial destination free flyer contract to start developing these commercial space stations. We're actually teamed with Blue Origin, and we're developing this space station, and we're calling it Orbital Reef. Think of it as a business park in space. Businesses come in, you provide the ecosystem, the power, the modules, the research facilities or the manufacturing facilities, tourist facilities, media, filmmaking, all of that kind of stuff. You provide the logistics and the transportation. Basically go to a company and say, what business do you want to do in space? We'll take care of the space part.
So when we think about another space station in the future, there's going to be different ways to get there, I'm sure, and one of them is Dream Chaser, product of Sierra Space, and that's really your project, right? That's your current project that you're working on.
in, matter of fact, 24/7 production on the first vehicle right now. And we plan to fly first quarter of 2023.
Oh my gosh, well, we have one here, so
I know.
let's go look at it.
Looking at all the airplanes I flew and then ones I didn't get to fly. I flew that one, I've flown that one, I've flown that, I've flown that, I've flown this guy. I've flown one of those too, yeah. So the Dream Chaser is a what's called a lifting body spacecraft. It's what we're working on, it's what we're building right now that we intend to fly in early 2023. What it is a lifting body spacecraft. And what that means is most airplanes, the wings provide the lift. I think most people know that. But in this particular vehicle, it's the body of the spacecraft itself that provides the lift, and only a little bit comes from those wings. So it looks like a mini space shuttle, right? So it's designed to launch on a rocket, fly up in orbit, rendezvous, dock, free flight, whatever you want to do on orbit, orbiting satellite, research platform. Then we enter, and when we enter, we see very, very high heating temperatures as we slow down, up to 3,000 degrees. That's why it's a blunt body. And then in the end, it comes down and it lands like an airplane. And so what I want is I want us, and quite frankly the whole world, to realize that commercial vision where space travel is routine. Multiple people going, thousands of people, tens of thousands of people working in space. I want to walk into a classroom as an astronaut and say, big deal. You know, half of our parents have gone to space.
Right,
Wouldn't that be awesome?
I think it's going to happen.
It will happen.
Yeah.
And we're doing everything we can to make it happen as soon as possible.
This was all kind of theoretical, even only 4 years ago. And now suddenly it's real, right? You've been to space already.
Going to space was life-changing. It really was. And as much as I told myself I shouldn't have expectations going into it, I really did. And those expectations were high, and they were just completely smashed. I mean, it was so much more profound and transformational than even I had hoped. So you're in the capsule about 35 to 40 minutes from the time they put you in to the time they take you out. So you're on the pad, and you would think you would be terrified, and you would think you would be scared, at least I thought I would be, and I really wasn't. So then you get to countdown, right? T-minus 10, which is like the classic space, 10, 9, 8.
7, 6, 5, 4, command engine start, 2,
Well, huge congratulations to all 6 crew. They have crossed that Kármán line and they became official astronauts.
You get to space and they do main engine cutoff, and then you're kind of floating in your chair, but you're held back from your harness. And then they do what they call capsule separation. But then you're able to unbuckle.
Cue the astronauts to unbuckle their harnesses and start floating around the capsule.
They are in 0G, they've practiced for this, and now it's really happening.
I had the privilege of going to the window and I turned myself upside down. And I did that intentionally to sort of disrupt my orientation of up and down. I looked out the window, I gasped. You're seeing the Earth from space, totally transformational, extraordinary. And then from there, you get back in your seat. That's quite important, because what's going to happen is as you go falling back down to Earth, you hit the atmosphere. And then you come on down, and then the first thing that happens is your drogue parachutes open. Those basically guide and settle everything down. Then you have the main parachutes deploy. Then once you land, they give the crew a private moment to huddle and hug each other and just bask in the experience that we just had together. And then they open the capsule door, and you're greeted by hundreds of press and your family and loved ones. It is shocking how much we were able to get done in 2021. The technologies have matured. I think I was number 606 human to go to space. I'd like to have 606 humans per year go to space. And I don't think we're too far away from that. I think that'll happen in this decade.
With that in mind, you started Space for Humanity a few years ago. Tell us about that.
Yeah, so Space for Humanity was founded with really 2 primary notions. One is that we need to democratize access to space. It can't be a a billionaire boys club. It can't be exclusively North American or white or anything. It's got to be human. It's got to be human endeavor. And then the second core principle was the notion that space is a tool for transformation, right? It's a lot of things, technical challenge, investment opportunity, but it's primarily a tool for transformation. It's run by a terrific leader named Rachel Lyons.
It's so good to see you.
Good to see you too. Let's go.
All right, I'm excited.
Part of the original mission was to make space accessible to anyone.
We have entered, just over the past few years, this new era in space exploration, and this new era in space exploration is very much being led by the commercial companies. Up until 2021, we had 8 people go to space commercially, ever. And in 2021, we had more than 20 people go. What the numbers are saying right now is that in the next decade, 10,000 people or more will have been to space. And this can't just be for the ultra wealthy right now. The potential of this is much too big. And just in this past year, I mean, it opened up to so many people.
Organizations like Space for Humanity are making it possible for anyone to apply to go to space. So it's really, ideally, eventually, not just for the wealthy.
Just in the past couple of years, we've had so many firsts when it comes to who's going to space and how they get there. People like Eric Ingram with different abilities, whether physical or mental, whatever it is, these are people that before never would have gone to space. And now with Mission Astro Access, they're learning things they never would have thought of before.
I applied to be an astronaut twice, knowing full well I would not be accepted. Imagine how many people aren't applying to be astronauts because they don't think they can meet the minimal requirements. As a species, we're at the very beginning of human spaceflight. And when you're at the beginning of something, it's the easiest time to design for things. And so Astro Access was founded to make sure that anyone can go to space when that opportunity presents itself. And so we flew our first parabolic flight in October of 2021, where we took a plane and we did some parabolas where we were able to experience microgravity and lunar gravity and Martian gravity, and able to test some awesome technologies and ideas we had for making space more accessible to everyone. I think what you're seeing with commercial launch companies and commercial space stations and all that is more opportunities for that larger set of the human race to be able to finally go.
Truly believe it. I know it's cliche, but you got to see it to be it. I know I didn't have that to see. And so by me being the first, maybe that'll make some other little kids say, hey, I don't have to be an astronaut, I could be a suit tech. There's space for everyone. It really is. And I truly believe that. I'm a prime example of it.
Startups are changing accessibility and sustainability in space, and even what it means to be an astronaut.
After half a century, NASA has plans to return to the moon.
The Orion Spacecraft is the vehicle that will take them to the moon.
While other players in the space industry set their eyes on Mars.
Clearly the real objective was Mars, and it's where the future is. It's the planet that has on it all the materials needed to support not only life, but human civilization.
Each breakthrough brings humanity one step closer to becoming a multi-planetary species, exploring further than we've ever gone before.
I think ultimately the Artemis program is really just about humans' enduring drive to explore. Hopefully through the Artemis program and through Orion, we'll unlock some secrets to the universe.
I'm Krajnovic.
And I'm Myrna James.
It's time to go behind the wings.
In this episode, we're going to explore the question, back to the moon or straight to Mars? It's not the first time we've been to the moon, but this time it's going to be different.
It's been over half a century, and it will be different. It's about going back for good to set up a lunar base, the CIS Lunar Economy, a gateway. There's still a lot to learn.
It's really incredible. Artemis is NASA's plan to put people back to the moon and possibly be a base to go to Mars.
To start off, we talked with Mars Society founder Dr. Robert Zubrin, who's been thinking about pushing the limits of space exploration since he was a kid. Why is space exploration important, and how did you first get started?
Why is space important, and how did I get into it? I was 5 when Sputnik flew. And while the adults may have been terrified of Sputnik, I was delighted with it, because what Sputnik said to me was this was going to be true. This was the future, going to move into space, and I wanted to be part of it. It reflects a child's delight with the possibility of an exciting and amazing future. That is what we need. We need an exciting, amazing, lively, optimistic future. If we can expand into space, then we can all understand that there's no reason to kill each other fighting over provinces if by working together we can open up planets.
Welcome to Lockheed Martin. Thanks for joining us today.
Yeah, happy to be here.
Kids are unique in that they just have this innate curiosity and wonder and sense of exploring it. It's something that we sometimes lose as we become adults. You know, they walk outside, they're the first to look up at the sky and to point out the moon. They just want to ask why. They just want to explore and understand things and see what's next. And I think on us as adults, that's part of our job, is to keep fostering that sense of curiosity and that wonder. I'm Heather McKay. I'm the Engineering Development Senior Manager on the Orion Program. Astronauts have been to the moon before on the Apollo program, but really that was just the initial step when it comes to exploration. There have been many famous explorers in the world. You think about Lewis and Clark, Magellan. And just imagine if they turned around at the first obstacle or even the first island that they found. And that's kind of where we're at with space exploration. The Apollo astronauts were great explorers, and Artemis plans to really pick up where they left off.
The plans to go back to the moon are ambitious. Everything they want to build there, the infrastructure on the moon, is going to take a lot of launch capabilities.
Yeah, it's a lot of mass, it's a lot of capacity, and the early rockets, they had trouble even just reaching that escape velocity, right? How fast you have to be going to escape the gravitational pull of an object. And this plan just takes that to the next level. You're not just launching people, you're launching all the infrastructure to build a permanent base on the moon. It takes some big rockets, like this one. We've gotten in touch with Tory Bruno. He's the CEO at United Launch Alliance. They're building the upper stage that's gonna take humans back to the moon for the first time in half a century. You know, we'll meet him at the Mission Control Center. I think he can tell us what it's all about.
Last time we went to the moon to explore it briefly, to go there a few times, and then we stopped. This time we're going back to stay. I'm Tory Bruno, the President and CEO of United Launch Alliance, and for the balance of our time together, I'm your personal rocket scientist. Big differences since the last time we went in the Apollo program, and mostly in the upper stages. So today we can fly much more complicated missions. When that Saturn V went to the moon the first time, it was a big deal that the third stage, with its J2 engine, could actually burn twice after a short coast. Now we can do lots and lots of burns. We can do long multi-hour coasts in between, and when we put that together with the tremendous computing power we can put on a rocket today, we can take more mass there, we can go faster, it's safer for the crew. So those two big technologies, the advanced upper stage and these powerful, powerful computers, I mean, your watch has got as much computing power, if not more, as we went to the moon with the first time. Imagine what we can do now.
In Greek mythology, Apollo had a twin sister. Her name was Artemis. And this program is named after Artemis, the goddess of the moon. And it's apropos, given the time, Artemis and the Orion Spacecraft will carry the first woman and the first person of color to walk on the moon. We are the Artemis generation. With the Artemis program, NASA plans to build a sustained human presence there. And the moon has so many interesting things. It's got interesting geology and craters from when the universe was first created. It has water ice that we can use for future fuel and propellant on future missions. And ultimately, it's this proving ground where we can test out our equipment and our technologies and our tools to prepare us to send humanity deeper into space.
This is very much an important moment in human history because it's going to change the destiny of our species. As we sit here on Earth today, we're living on a planet with limited resources, and we're putting a lot of attention and our thought into how do we live a smaller footprint to extend the inevitable consumption of our planet's resources and the collapse of our society and our civilization. This changes all of that future for us.
There is incredible natural resources on the moon and on the asteroids or near-Earth objects, as we call them, that are within easy reach of the moon in this greater space we call CIS Lunar Space. There is such an abundance that it literally defies human imagination. And when we are able to tap that, it changes everything for us. A post-scarcity human future is what we're looking at. You know, putting a 50-story building on a launch pad that is 90% high explosive to just break the bounds of gravity, right? Defying the tyranny of our planet's gravitational force to hold us down is impossible, and yet we do it all the time. It's become routine. When we look to the potential future for humanity and for the entire globe that exists through the moon, through that gateway to these resources, you're just so inspired by it. You're not daunted. You just have to go do it.
We're here in Houston, Texas, home to Johnson Space Center, NASA's Center for Human Flight. There's so much cool space stuff here that in 1967, it earned the nickname Space City. We met up with Jim Jeffrey, who works on the Orion spacecraft.
My role is to be the Vehicle Integration Manager for Orion's Spacecraft program. Orion is the spacecraft that's going to take humans back to the moon for the first time since early 1970s, and they'll do so on the Orion capsule. Starting with the International Space Station program, we've had a continuous presence in orbit for over 20 years, and we're using that to develop long-duration technologies, understand what it takes to keep humans alive for months in space. And now this summer, we're going to launch the first Artemis mission. Artemis 1 will be a crewed test flight, could be 4 to 6 weeks long. And what we're going to do is launch the Space Launch System and Orion for the first time and take it out to lunar orbit. We'll test out all the technologies that are needed for safe crew exploration and demonstrate that we're ready to put humans on board on Artemis 2. One of the hardest things about the Artemis program is the integration. All the different pieces coming together at the same time to accomplish one job, launch our astronaut crews to the moon and back. So that requires a lot of integration, coordination, and communication across the country and really across the world with our European partners. They're all contributing to help Artemis be a success.
The Orion spacecraft is very complex. It has thousands of parts, and it's specifically designed for these very complex missions to deep space. So this is a small-scale mock-up of the Orion spacecraft. You can see some of the key elements. The big blue things are the solar panels, so we can provide power in deep space. You see the small squares, those are the windows, so the crew can look out and see where they're going. On top of this would be the launch abort system that jettisons at launch. It would reveal the docking system so we can dock to the gateway and the human lunar lander. On the back end would be the booster, that Space Launch Systems that falls back to Earth once it does its job on launch. It's really a state-of-the-art spacecraft and part of the next era of human spaceflight. Lockheed Martin is the prime contractor to NASA building the Orion spacecraft, but it takes a whole team around the world to make it work. Lockheed Martin has over 2,900 subcontracts with businesses in every state of the country, many of them small businesses. We also have international partners. The Europeans are building the service module. Men and women are working hard all over the country to building the spacecraft, getting it ready to take people to the moon.
It is so cool to be going back to the moon with people after half a century of not being there. ULA is participating in a couple of different ways. We're going to fly one of the early robotic uncrewed missions, something called the Peregrine Lunar Lander, which is really cool in itself because it's the first commercial lander to the moon. And then we're also part of SLS's first missions. We're providing the upper stage, the interim cryogenic propulsion stage for Artemis. So we're just really excited to be both a part of the uncrewed missions and part of the activity leading to the crewed missions when people will go to the moon and put boots in the regolith finally after 5 decades.
The Space Launch System is a very versatile and capable system. It was developed using systems that are derived from the Space Shuttle program. The solid rocket boosters that people are familiar with, the big orange tank in the middle that holds the propellants. The main engines are formerly known as Space Shuttle main engines. So using the development work we've done previously in that flight experience, we're now using them in different ways in order to support a different mission, deep space exploration. So the SLS is capable of launching the Orion spacecraft. It's also capable of developing a cargo configuration where we could put very large payloads into space.
There'll be a space station orbiting the moon. There'll be permanent facilities on the moon. There will always be a continuous human presence on or at the moon, much like the International Space Station today. That means logistics is everything. There's cargo, there's fuel, there's water, there's trash coming back, there's toilet paper and coffee. This is going to be a huge job to support those people who are exploring this really important body right here, just a week away from where you and I are sitting here in our control center.
We're in the operations center, and what exactly goes on in here? Because I imagine on a launch day, we have lots of chairs and computers. They're usually full of people.
They are. There's a person in every chair on every monitor, and this room is actually supporting the mission control center that would be down at the launch site. These are full of engineers. Every part of the rocket has an engineer personally responsible for it, and they're on this during the countdown. They're monitoring telemetry on the pad from their equipment. Wow. They can, on these screens, get all the data for that piece of hardware since the dawn of time. They can make sure everything is good, and if it's not, they'll huddle up in this room and they'll solve problems.
And give me a sense, what would this room look like on Artemis 2 launch day?
You can see the headsets, they'll all be on there. They'll have all kinds of data on their screens. They'll be talking amongst themselves, making sure everybody's comfortable or solving problems. You'll hear comms going back and forth. Like these little devices will allow us to tune into different channels. There's so much happening. It's a giant orchestrated effort.
So many firsts have happened in here, and with the Orion and with the Artemis missions, there's going to be more. Do you ever get used to it?
No, never. So we're at over 140 launches now. We'll be up over 150 here shortly here at ULA. I personally, across my career, have done close to 400 launches. And I'll tell you, it never gets old. It never gets routine. I get butterflies every single time.
Wow.
There's nothing like it.
Well, Tori, thank you very much.
Thank you.
I think we're in the early stages of space exploration. There's a lot more to learn about how to operate in a deep space environment for similar lengths of time. We're developing now the systems with Orion to take people to deep space exploration destinations and bring them back. So the upcoming Artemis missions will be the early demonstrations of those capabilities, but there's a tremendous future ahead for us to go explore.
My name is Jackie Mahaffey. I am the Chief Training Officer for the Artemis 2 mission, so our first Orion crewed mission. And my job is to lead the development and execution of the training of our astronauts that will be on that mission, as well as the simulations that we will provide for the mission control team and when the mission control team practices with the crew together. All of the astronauts that we'll be taking for our Artemis missions will have had our astronaut candidate training or equivalent if they're an international partner crew member. So we have some baseline that we can expect from them in terms of understanding spaceflight, understanding how teams work cohesively, and then from there we look at what are all the different tasks that the crew is going to have to perform on the mission.
So the Orion spacecraft, this is a big part of their training. Should we take a closer look?
Yeah, let's grab our helmets and head in.
All right.
You can see the 4 seats and the configuration, they have them here. What you may not be able to see, if you look behind you, you can see, are the display units. So these seats here are for our commander and pilot, and they will be, during pre-launch and during launch, monitoring the data coming from the launch vehicle as well as the Orion vehicle, and just understanding everything is going well or communicating with mission control about something that may not be going as planned. First couple missions, Artemis 3 in particular, will be about proving our capabilities to land on the moon and exercising all of the new equipment, new spacesuits we have to go explore the moon. Artemis 4 folds in the gateway, that outpost that will be around the moon. You know, we're going to practice having that as an outpost to support our lunar missions, and we will learn a lot about how we can use an outpost like that to help support our missions to Mars one day.
This is basically a deep space station. It's a much smaller version that will orbit around the moon. It'll allow astronauts to do extended missions above the moon, to and from the moon, and for Orion to dock and return. When they're not exploring the moon or in Orion, they'll be able to do this deep space science that will enable us to further explore deep space.
So once the astronauts are suited up, one of the first things they'll do is come in and get strapped in the seats. Is that something we can try out?
Yeah, sure.
So how do you get into these seats?
Put your feet up on the footrest. I have a little extra strap with me.
And I mean, now it feels like a very kind of awkward position, but if you're in zero gravity, it won't feel quite so awkward maybe.
Yeah, although remember, they'll be in this position for launch and entry. This is like the total extent of switches, which if you've ever seen the inside of the space shuttle, it was covered with switches and circuit breakers, and so most things are operated through the display panels.
It is just really cool to think that this is kind of the setup and situation that the next humans are going back to the moon and maybe one day Mars. So that was really cool. Thanks for showing me.
Yeah, absolutely.
All right.
Watch your head. For me, going back to the moon after 50 years means a lot because my generation never saw that happen live. And I grew up knowing the space shuttle and being familiar with it, seeing us be on ISS on the space station for over 20 years. And those things feel very normal. But knowing that this really cool thing happened and never having seen it live, I'm personally really excited about, like, let's see it happen again. And then let's do even more.
It's a big question. How do you decide moon or Mars?
There's really two main camps to answer this question. The first camp, of course, is NASA and the Artemis Program, with an incremental stop at the moon in order to get to Mars. But that way people can get used to living in space and they have this incremental option. And the other option is straight to Mars.
Straight to Mars, it sounds pretty good to me if it's doable. It's not really a new idea. Robert Zubrin and others actually proposed this in 1991, something called the Mars Direct proposal. And part of it is the idea that Mars is just a very interesting planet to go to, the atmosphere. There's a lot you can do there. You can make the fuel, you can make water, and it sounds like a good place to live. You know, today Elon Musk and others have kind of adopted their own version of it. Elon with SpaceX and Starship, which is the ship they're building to make trips to Mars. So the Mars dream is not dead in general and for NASA as well.
Do we go right to Mars? Do we go back to the moon and then go to Mars? I'm more of a moon first guy only because it seems, somewhat kind of serendipitous that the moon is there, 2 days away instead of 200 days away. The moon has, a sixth of the gravity of Earth as compared to Mars having a third of the amount of gravity. The moon has no atmosphere, which in some ways can make things easier. Other things makes more challenging.
The moon holds a lot of secrets. We want to go to new places on the moon that we weren't able to explore during the Apollo missions. Places where the sun has never shone, and we may find early parts of the solar system captured in these extremely cold craters around the moon.
While Orion has been built for the Artemis program and these lunar and deep space missions, ultimately we believe it has a place at Mars too. We believe the Orion spacecraft can be used for up to 1,000 days, which is just about how long it would take for a mission to Mars. And Lockheed Martin has this concept called the Mars Base Camp, where it uses Orion as a cornerstone and then adds habitats and other things that are needed to explore Mars. It might be possible someday we need or want to become a multi-planetary, faring species. And along the way, we'll do some interesting science and we'll develop technologies that will help us here on Earth and inspire the next generation.
It seems like the moon was perfectly placed for us to practice, to learn things that will help us go to Mars someday. Now, having said that, it's expensive. And, you know, if you have to make the choice, do I do both? Do I just do one? How much money do I have? You know, maybe you could make the argument that, you know, bypass the moon and go on to Mars.
Clearly the real objective was Mars. Mars is where the science is. It's where we're going to discover the truth about the potential prevalence and diversity of life in the universe, and it's where the future is. It's the planet that has on it all the materials needed to support not only life, but human civilization. For us, Mars is the new world. What's the fastest way there? Mars Direct.
And then a journey into tomorrow, a journey to another planet, a manned mission to Mars.
NASA in 1989, the first President Bush called upon NASA to implement a program, return to the moon and on to Mars, and this time to stay. It was the 20th anniversary of the Apollo moon landing, and that's how he celebrated it. And so NASA went off and developed a plan that was gigantic in its cost and schedule. They're making this much more complicated than it needs to be. It's like, you know, designing a school play to make sure all the kids have a part. It's great for school play, but when you're talking about tens of billions of dollars, it starts adding up. The concept was immediate, caused a lot of excitement, and it immediately became controversial. There were a lot of people in NASA and even among our competitors who thought this was great. This is a way we can actually get to Mars. Technologically speaking, it was within the realm of our technology in 1990 when we came up with the plan, and it still is. Along comes Elon Musk. Now, he's certainly not interested in doing things to spend money. He's interested in spending money to do things. So he has embraced a version of the Mars Direct plan as the basis for his plan for human Mars missions. The designs of the vehicles are different. They're his own designs. And there are certain aspects of the plan that are different. But it's basically direct flight to Mars, no on-orbit assembly, no need for other orbital infrastructure, and direct return from the surface of Mars using propellant made on Mars. That's Mars Direct. That was the plan that Baker and I laid out in 1990, and that is the plan that Musk has embraced in his own way today. We are most likely to get to Mars this decade. Once Starship becomes operational, Starship uses methane oxygen propellant, and that is why it uses that instead of other possible propellants, because it's the propellant you can make on Mars. Heavy lift vehicles using propellants that could be made on Mars, regularly flying to Earth orbit with payloads comparable to that of a Saturn V moon rocket, but 1% the cost because it's reusable. He's got the transportation system, that's the main thing. We develop everything else. Put this together, a public-private partnership, we could be on Mars before the end of this decade. And that is what I think will happen.
My name is Dr. Shannon Rupert, and I'm the director of the Mars Desert Research Station. The Mars Desert Research Station was built to study what life would be on Mars, how we as humans would not only live, but explore and do science. We're in a true geologic Mars analog. What that means is that you see the same patterns and processes in the geology of the area where the station is set that you see on Mars. The idea is when you put humans on Mars, they can get so much more information than we can get from a single robotic mission.
We asked so many people in the space industry what their dream is for the future of space exploration. Engineers, astronauts, entrepreneurs, historians. It's a great question because there's not just one answer.
My hope is that NASA and the Artemis program can help make humanity be a multi-planet species.
I want to see the space industry get to a point where we can access the infinite resources of space.
Just forget about Moon and Mars. I think we are on the upward swing of more common access to space than we've had previously.
Ordinary people like you and I will live and work in space because our jobs are there and we can have a better life there.
There are so many smart people working on this question, what is the future of space exploration? And the only way that we can realize that future is by dreaming and working together.